We just got back our chapter 18, 19 circuits test, and we're not very good at capacitors. So let's fix that. Most missed problem on the test had to do with capacitors, and it went along somewhat like this. Imagine that you have some circuit that branches parallel with this capacitance setup, okay? And let's give these some quantities: 9 microfarads, 3 microfarads, 6 microfarads, okay? Here's the question. If I measure the potential across all of these capacitors, remember, we have to measure potential in parallel here, okay, because we're measuring what's this versus what's this. If I measure the potential across all of these capacitors, how could we rank them? Which one's the greatest, which one's the smallest, okay? And this is how we think about this. We need to go back to the idea that Q equals CV, okay? And if we're looking for, where this V is the voltage, it's the voltage difference across the capacitor. So that means V equals Q over C. Okay, so let's think about that for a second. If we are looking at this, then what we're thinking about here is from this point to this point, there's the same potential drop. So if I said on this side there's like 10 volts sitting here, and on this side there is 0 volts, it's less. I don't know if it's actually 0, it's just less, okay? From here to here, that drop of 10 exists, but if we think about how the pathing has to go on this, that means from here to here, we are going from 10 to 0. Going from here to here is going from 10 to something that's not 0, okay? And then we're going from that something to 0. So right off the bat, when I look at my largest potential drop, it's the 9 microfarad. So the 9 microfarad capacitor has the largest voltage drop, okay? So that voltage drop of the 9 is greater than everything else, just by logical reasoning in that regard. Okay. If we then consider some things we know about the capacitor, when I have capacitors in series have equal charge distributions on them. Okay. Series caps equal charges. How about yield equal charges? So if this has a charge here of, I don't know, 4 coulombs, this also has a charge of 4 coulombs. You just can't get away from it. And that's just the way they charge up. For every charge you get here, you instantaneously get one here. So because they charge like this, they charge simultaneously, generally speaking, they have the same charge, okay? Once this one fills up, you can't get to this one. Once this one fills up, it doesn't even matter. It's just broken circuit. You're done. So they charge equally. Since they have equal charge, Q of 3 equals the Q of the 6, but they have different capacitances. What we can say here is Q3 equals C3, and then the voltage across it, which means that the voltage equals Q3 over C3. For 6, we can say that Q6 equals C6 times the voltage across it, which means that its voltage, and this I guess is of 3 and 6, equals the charge on 6 over the capacitance of 6. Well, if they have the same Q, that's just some constant. Let's just make it 1 for ease of purposes. then because this has a smaller capacitance, that is actually going to create a larger potential difference. Look here, the voltage and the capacitance have an inverse potential. So a smaller capacitance, that's actually going to leave a larger voltage. Because this has a larger capacitance, it's going to have, with respect to the third, a smaller voltage. So it's actually going to go our 9 microfarad capacitor first, then we're going to have the third, and the third is going to be bigger than the sixth. That's how that you do that, okay? It's just using this equation right here, rewriting it into this, identifying the 10 to 0 immediately, or whatever it is, recognizing that you have 2 steps here, and then understanding that in series, capacitors have equal charges. That's an important thing for us right there, okay? That's a little tidbit of the night. Maybe I'll drop one of these on by the end of the night. But for right now, that's what we got. Okay? Until next time.